Okay, I want you to imagine a world where you can steer a 2-ton vehicle, communicate really complex ideas, or navigate a digital landscape, and you're doing it using absolutely nothing but your thoughts. I know, it sounds exactly like a distant sci-fi future, right? But what if I told you that reality is actually already here? Welcome to this explainer. Today we are unpacking the incredible, fast-moving science of brain-computer interfaces, or BCIs. We're going to explore the fierce philosophical tech battle shaping the industry right now, the immense technical hurdles standing in the way, and a recent breakthrough that might just put this kind of technology in your living room way sooner than you ever thought possible. Let's dive in.
So this isn't some Hollywood CGI or a movie prop. We're talking about a real, physical, experimental vehicle being driven outdoors by a human being's actual brainwaves. In a fascinating study out of the University of Cambridge, researchers successfully used what are called steady-state visual evoked potentials to let a driver control an SUV. Basically, the driver wears an EEG cap, they focus their eyes on specific visual frequencies, and the computer instantly translates those neural signals into moving and braking commands. This really sets the incredibly high stakes for our explainer today. We aren't just talking about, nudging a digital cursor around on a screen. We are literally talking about mind-controlling heavy machinery in the real world.
Part 1. Two paths, kernel versus Neuralink.
Okay, let's really get into this, because to understand where this entire industry is headed, we first have to understand the massive tech rivalry that is currently defining it. The race to map the human brain has basically split into two totally dominant but opposing philosophies. On one side, we have Elon Musk's Neuralink. Now, their approach is highly invasive. It requires the surgical insertion of microscopic computer components directly into the brain tissue itself. The goal there is to get as physically close to the actual neuron firings as possible. But then, on the exact opposite side of the spectrum, we have Brian Johnson's company, Kernel. Kernel's approach is entirely non-invasive. They're building these wearable caps packed with advanced sensors that read your brain activity straight through the skull. They are prioritizing accessibility and totally avoiding the need for brain surgery. And listen, both of these companies have spent hundreds of millions of dollars betting that their path is the one true way forward.
Brian Johnson himself actually explains this fundamental trade-off brilliantly. He says, Neuralink is a circle on the screen in 4K. Kernel is the full movie in 1080p. I mean, that is just the perfect metaphor, right? Because Neuralink physically implants electrodes deep into specific regions of the brain. The data they pull is incredibly crisp, clear, and high resolution, but it's hyper-localized to just that one small area. So a highly detailed circle on a screen. Kernel's wearable tech, on the other hand, covers the whole head. It gives you this much broader picture of your entire brain's activity, the full movie, basically. But because it's reading all that data through bone and tissue, the signal is naturally a bit more muffled, so it's in 1080p rather than 4K. It is a really profound engineering trade-off.
Part 2. The hidden enemies, system latency, and calibration.
Now, while their hardware philosophies couldn't be more different, both paths face the exact same monumental roadblocks that are keeping this tech out of your home right now. Behind all the futuristic promises, there are massive technical hurdles that engineers are sweating over every single day. The first hidden enemy? Time. Specifically, 100 milliseconds. According to comprehensive technical reports across the market, if you want a genuinely natural experience, whether that's controlling a prosthetic arm or driving that SUV we talked about earlier, the end-to-end delay, from the moment you think the thought to the moment the machine actually reacts, has to be under 100 milliseconds. But here's the reality check. Current BCI systems typically lag anywhere between 100 to 500 milliseconds.
If we break down the processing pipeline, it makes total sense why that lag happens. First off, just to acquire a reliable signal, the system needs to listen to your brain for about 200 to 300 milliseconds. Then, extracting the meaningful features from that raw signal, that adds another 50 to 100 milliseconds. And finally, running all that complex data through deep learning classification models adds yet another 20 to 80 milliseconds on top. When you add all this up, you're looking at a massive delay. Imagine driving a real, physical car, seeing an obstacle, thinking, brake, and the car literally waits a full half second before actually hitting the brakes. In real-world, time-critical scenarios, a lag like that isn't just annoying, it is absolutely terrifying.
And then we have the second hidden enemy, which is calibration. With traditional setups using those really cumbersome BCI electrode caps, you can't just slap the device on your head and start playing a video game. Every single human brain is entirely unique, so that means the computer has to be custom-tuned for hours just to figure out how to read your specific neural patterns. It's a long, tedious, totally exhausting process for everyone involved. And the worst part? If you take the cap off to go to sleep and put it back on the next day, you often have to do the whole recalibration process all over again.
This brings us to a really pivotal crossroads for the entire field.
Think about it. If we have to surgically implant devices into people's skulls, or spend hours custom calibrating these massive caps every time we use them, all while dealing with dangerous lag, this technology is never, ever going to reach the mainstream. So the ultimate question is, how do we make this universal? How do we build something that anyone can just pick up, put on, and use?
Part 3. The universal calibration-free breakthrough. Well, the answer to that big question might have just arrived, thanks to a massive breakthrough by engineers at the University of Texas at Austin. They have essentially created a one-size-fits-all brain-computer interface that completely bypasses that awful, tedious individual calibration process we just talked about. By utilizing a highly sophisticated machine learning decoder, the interface actually learns and dynamically self-calibrates through repetition, all in real time. This means the system can seamlessly shift from one patient to another without needing a specialized medical team to come in and retune the hardware. And to prove it, they actually had 18 test subjects put on the electrode cap, completely skip the long calibration, and immediately start navigating a Mario Kart-style racing game using absolutely nothing but their thoughts. I mean, it is just an unprecedented leap forward for accessibility in this space.
Part 4. The new brain ecosystem.
Because you see, once we solve the latency and once we bypass the clunky calibration, we move past the raw hardware into something much, much more profound. Actually, the hardware is really just the dial-up modem of the 90s. Think about the early internet for a second. That screeching dial-up connection wasn't the end goal, right? It was merely the gateway that birthed the entire web, email, streaming, social media, the whole shebang. Brian Johnson argues that current BCIs, whether they're invasive like Neuralink or non-invasive like Kernel and that UT Austin cap, are just the modern equivalent of those old dial-up modems. The true, lasting value won't just be the headset itself. It's going to be the entire ecosystem of apps, games, and incredible medical aids that will be built on top of this direct brain connection.
And we are absolutely already seeing that ecosystem mature. We're moving from simulated virtual environments like the computer model of the car in the Cambridge study or that Mario Kart game at UT Austin, straight into the tangible physical reality. These models are now being applied to a real SUV driving down a road, or, as they brilliantly showcased at the South by Southwest conference, using thoughts to directly control hand and arm rehabilitation robots. As that latency drops down to that critical sub-100 millisecond mark, this technology definitively shifts from just playing video games to fundamentally transforming the lives of individuals with severe motor disabilities, finally giving them back their agency and independence.
Which really leaves us with this final lingering question. We've explored the two wildly different paths of invasive and non-invasive tech. We've seen exactly how machine learning is conquering the hidden enemies of lag and calibration. We are quite literally standing right on the precipice of a brand new era of human evolution. So what happens when our minds are seamlessly, instantly integrated with the digital world? Is it going to change how we communicate, how we work, or maybe even how we understand human consciousness itself? One thing is for sure, this tech is no longer science fiction. It is simply a matter of time. Thank you so much for exploring this with me today, and definitely keep your minds wide open to the future.